Hi, my name is Francis Jackson. I'm from Liverpool John Moores University. Today I'll be presenting my paper towards practicable digital twin workflow for bridge asset management study in Scotland. I produced this paper in collaboration with my colleagues Maria Ferentinou and Michaela Gkantou. Just a quick outline of today's presentation. First, I'll talk about the background to this study and the challenges facing transfer industry in the UK. I'll then move on to talk a little bit about the case study we chose, the workflow we devised, and the outcomes of our research. There is serious concern of the vulnerability and resilience of transport infrastructure in the UK. Transport infrastructure in the UK is fully under threat from age-related deterioration, as many assets date to the last century and approaching the end of their intended design lifespan. Climate change-induced severe weather, the effects of which were not captured in assumptions made at the time of design and construction of these assets, and resistance to constructing new infrastructure generally, as the physical environment in the UK is constrained and there is a strong desire to extract all utility that is possible and safe out of existing assets. This is a big issue because infrastructure failures, when they do occur, are not isolated. They tend to propagate across transport networks and various sectors of the economy and society, and their effects can be felt far beyond their initial location. So, digital twins are one means of addressing these threats that has been proposed. Digital twins are difficult because there's no single widely accepted definition. So, a definition that's popular in the UK is that proposed by the Centre for Digital Built Britain in 2018, which is that digital twins are a realistic digital representation of assets, processes, or systems in the built or natural environment. But you can appreciate that isn't very descriptive of digital twins themselves. So I think it's easier to think about digital twins in terms of their characteristics. So digital twins should provide a continuous and dynamic representation of asset state. And what this means is that there are bidirectional data flows between an asset and its digital twin. So you have data flows from the physical to the digital, that is from the asset itself to the model, and that means that the twin is synchronized with reality and reflects reality. And you have flows from digital to physical, and that is where the digital twin is used to actively influence or control the operation of the asset. So you're taking the lessons learned and insights gleaned from the digital twin and carrying those through to the operation of the asset. So crucially, in a digital twin, data flows should be real-time and continuous. The data should be live and give an up-to-date representation of the asset. So the key aspects really are data, modeling and data integration, prediction, that is using the current state of the asset to think about how it might behave or perform in the future, and decision making, using the insights and data to make better decisions. So neglecting or overemphasizing any one of those aspects will lead to a less powerful digital twin. If you emphasize the modeling at the expense of the data, you're going to have a digital twin that looks really pretty, but does not lead to effective decision outcomes. And equally, if you overemphasize data, you lose some of the power of digital twins, which is that ability to interrogate data in association with the model that gives you that visualization. So with my research, I aim to develop a proof of concept digital twin of bridge in order to explore how that could unlock opportunities for enhanced asset management. And that is about recognizing the potential of digital twin as a powerful tool in infrastructure asset management and setting out a workflow for the post hoc after the fact twinning of existing assets. So the key objectives for this work were to incorporate monitoring processes, and that means giving a real-time picture of asset state, incorporating predictive processes, having that analytical capability built into digital twin in order to interpret that data, and for the digital twin to be effective, that is leading to better decision outcomes for asset managers, affordable, that is not relying too much on specialist hardware or software, interoperable, so it should be able to engage with different platforms and data sources, and repeatable. So you should be able to take this workflow and apply it to other assets in the same way I did to our case study asset. So in order to demonstrate this workflow, I created a digital twin of a case study asset, which is a bridge crossing the River Fyne in Scotland that is part of the A83. So there you can see the location of the bridge asset in the UK on the west coast of Scotland. The bridge asset exists in an area that is particularly exposed to climate hazards that are expected to worsen in the future. There you can see the bridge itself. It's a pretty good, typical representation of the kind of assets that exist on the UK road network. It dates to the mid-20th century. It's a four-span reinforced concrete bridge. And I was able to model the bridge geometry because of historical design drawings that were provided by Transport Scotland for this purpose. Here you can see the software ecosystem that the workflow uses. So with those objectives in mind, namely affordability, interoperability, and repeatability, we chose to use tools that were already widely available and used by organizations in the UK, and that is the Autodesk AEC package. So for 3D modeling, we used Revit and Civil 3D to capture the geometry of the bridge and the local terrain. We used Autodesk's dedicated digital twin platform, Autodesk Tandem, to host digital twin and the different data sources for data or generation and orchestration between the digital twin platform and external sources. We use Tandem Connect, which is a built-in modular coding system that exists to complement Autodesk Tandem. And then for the analysis, we used a Google Sheets spreadsheet. So let's break down the software ecosystem a little bit, and I'll show you some of the outputs at different stages. So the 3D modeling, as I mentioned, was done using Revit and Civil 3D. So we were able to model the bridge based on the historic design drawings provided and the local terrain based on open source map data. The bridge doesn't feature an operational sensor network, so we generated data, generated real synthetic data using a Tandem Connect pipeline. That data is then orchestrated, pulled from digital twin via a second Tandem Connect pipeline, which makes a HTTP call to a Google Apps script, which is able to transfer the data to the Google spreadsheet. And there you can see the parameters for the analysis calculations the latest parameters are reflected in the Google spreadsheet. And then a third Tandem Connect pipeline takes data from the Google sheet and feeds it back into digital twin. And there you can see some examples of the digital twin in action, as it were. So we've got our time series data dashboard, and also with threshold lines set up to see where data, you can see where data exceeds the thresholds, and also an alert where a threshold has been exceeded in the model itself. So there's an amber warning attached to the bridge. You can see how this might be useful for asset managers to flag issues with performance immediately and very clearly. So here you can see some of the outcomes of the analysis function of digital twin. On the right, you can see a successfully run Tandem Connect pipeline that has pulled the relevant parameters out of digital twin and fed them to the Google Sheets application. And on the left, you can see the outputs of those analysis calculations reintegrated in the digital twin. So you have bending utilization and shear utilization indicators that are in the digital twin as a result of the analysis and associated with the bridge deck element. Okay, so now we can think about some of the outcomes of the research. And we can really think about the workflow in terms of 5 dimensions, which are broadly in line with the objectives we discussed earlier. So first, monitoring. The asset state data was visualized over time and linked elements, but the main constraint here was the synthetic inputs, so that we weren't using real data. And this means that although we demonstrated information handling, we didn't get to stress test the workflow with the integration of real sensors, and it does therefore lack some realism. There was also the prediction or analysis, and we did successfully integrate representative analytical outputs into digital twin associated with the bridge deck. And the main constraint here was that this analysis is very much simplified, and although it does demonstrate a modular analysis reintegration pathway, it's not very complex, and other more sophisticated platforms may be useful for a real world instance of this workflow. In terms of interoperability, we were able to demonstrate bidirectional data exchange where parameters preserve their meaning throughout the process. The main constraint here was that they were platform specific, so although the workflow operates, it remains attached and bound to the ecosystem. In terms of practicality, we used no commercial tools and didn't require any kind of specialist compute infrastructure. So the main constraint here would be the licensing and setup burden. You would need to procure all this software. So this was quite feasible at the proof of concept scale for a single asset, but I could see that being more difficult to scale up. And also repeatability. So the schema we defined and the workflow pattern is reusable in principle, but the main constraint here is that it is specific, asset specific for the geometry and analysis. So it's transferable in principle, but it's not asset agnostic and would require some fine tuning if it were to be applied to other assets. So now to discuss the limitations as well as the benefits we discovered of this workflow. It is able to incorporate data analysis platforms in a way that is accessible and adaptable to people that might be building up this system. It does not prioritize 3D model geometry at the expense of producing actual insights. The emphasis is not on the model, although it is still able to achieve effective visualization. I think one of the best aspects of this workflow is that it is fully automated, so it takes humans out of the loop, and this kind of hands-off approach makes data management easier and more consistent, especially over the longer term. It uses commercially available software that's already widely used in the industry and quite simple sub-workflows, and this is going to make it easier to operationalize on a larger scale and helps to overcome skill gaps. However, there were limitations to this workflow. The workflow still requires significant organizational capability to provide them with the software, and there are issues with vendor dependency, particularly for long life assets. So in terms of takeaways, I think we demonstrated that it is feasible to create digital twins of existing assets post hoc and after the fact, and this will be useful for managing assets going forward. That said, digital twins are not a silver bullet or panacea that can fix all issues affecting transfer infrastructure. They rely on good data and good modeling to produce actionable insights. So I would say the benefits digital twins in our workflow are real, and we have demonstrated them, but they are highly contingent. So in terms of future work to advance this research, I think it would be beneficial to transfer this workflow to other types of assets, other types of bridges, other infrastructure assets, introduce more complexity to the workflow, so trying to incorporate more data sources, different external analytical platforms, more complex external analytical platforms. And I think it would be particularly beneficial to test the workflow with real-world monitoring data derived from actual operational sensors. Here you can see the work we've referenced as part of this research, if you'd like to look into any of these sources further. And finally, thank you for listening.